Everybody. So linear regression, we have started talking about linear regression, and we said if you have basically two variables and you want to find a relationship between two variables and you want to quantify it, then you can use regression. We have different types of regression. We start with very simple case that we have both predictor and both response are continuous. As you can see, we have purity as response, and predictor is basically hydrocarbon level in this example. And what we do, we first plot a scatter plot to see if there is any relationship between them or not. If not, we don't bother. One thing we can do, we can calculate the correlation between these two variables. For example, in this case, this correlation should be close to 1 because it's basically positive correlation. When x increases, y also increases. And here is the equation for finding the correlation coefficient. It's also known as Pearson correlation coefficient. Pearson correlation coefficient. And one of your friends asked how basically we can do a hypothesis testing, and I added one slide. This is how we can do hypothesis testing, whether this is significant or not. So as you can see, H null is rho is equal to 0. Okay, so this is kind of like population correlation. And alternative, this is the typo, this should be alternative, is rho is not 0, which means there is a significant relationship between two variables. Okay, so what we do, we calculate rho hat, and then this basically quantity is our test statistic, approximately follows a t distribution with n minus 2 degrees of freedom. So if this guy is less than the threshold, we cannot reject H null. Otherwise, we reject H null, meaning that the correlation is significant. There is a relationship between two variables. Does it make sense? Any questions so far? So we can do some approximation. For example, if this is not R again, this should be rho hat. If rho hat is a small, then and n is large, then you can use this basically approximation, and your threshold would be 2 divided by number of observation, which is n. Okay, and because z alpha over 2, t when n is large, t and z gonna be the same, and z alpha over 2 for alpha equal to 0.05 is 1.96, which is around 2. And this is the number of observations, which is this guy here. Okay? And this is like absolute value. Okay? Because it's two-sided. And if rho is a small, then this quantity should actually it's going to be 1. Then I just left with this guy in numerator. Okay? That's why from here to here, we assume that rho is a small. If rho is a small, denominator is negligible. And if n is large, there is no difference between n minus 2 and n. That's it. Any questions so far? Okay. So let's see. Let me continue with basically simple linear regression. So what we want to do, after we figure out there is a relationship between two variables like y and x, now we want to quantify that relationship. Very simple regression method is called simple linear regression. It's linear, as you can see, and it's simple because we only have one x, one predictor. Okay? As opposed to multiple when we have multiple predictors. So what we want to do, we want to basically find a linear relationship between y and x. And this linear relationship is quantified by intercept and the slope. Okay? So your y is response, your x, sometimes we call it predictor, sometimes we call it regressor, sometimes we call it independent variable. Okay? Y, sometimes we call it response, sometimes we call it dependent variable. Okay? So this is intercept, this is a slope, and what is this guy? This is the random error. If this is the true line, this guy is random error. So the difference between the true line and the value that you observe. Okay? Any questions so far? So we assume that epsilon I is normally independently distributed. Okay? This is a strong assumption. For finding basically beta 0 and beta 1, okay, the only thing that we need is uncorrelated error with constant variance. So variance should be constant, this guy, and the error should be uncorrelated. So normality assumption is not necessary. Whenever you want to do a statistical inference, then normality assumption is important. Okay? So this assumption compared to assumption here is a little bit stronger because we have normality on top of that. Okay? Any questions? Yeah.
Do you also need summation epsilon I to 0?
No. No. That's a property of residuals that we will talk about that later. So the question is, summation of epsilon I should be 0. I said no, actually, because this is random variable. Okay? The expected value of epsilon I should be 0. Yes. Okay, so one question. Here I say uncorrelated errors. Over there I said independent errors. What's the difference? Anybody can tell me? So if two variables are independent, they are definitely uncorrelated. But if they are uncorrelated, it doesn't imply that they are independent. Okay? Only in one case this is true. Only in one case, uncorrelated, not being correlated implies independency. And that case is normality distribution. Okay? That's why if I add normality to this assumption, then it becomes NID, normally independently distributed. Okay. So another kind of like terminology that we use here is slope and intercept. We call them regression coefficient. So these are the regression coefficient that we are trying to estimate. How we want to estimate? So that's very simple. We want to estimate beta 0 and beta 1. And you remember I told you like different methods of estimation. One was maximum likelihood. One was method of moment. That's the third method. This is called least square method. Method of least square. What we want to do, we want to minimize the error of estimation. In this case, what we want to estimate? We want to estimate a line, and these differences are error of estimation. So we want to basically minimize the sum of a square of error. Does it make sense? Is it clear? So we want to find beta 0 and beta 1 such that the sum of a square of errors, this is error, this is error, this is error, be minimized. As you can see. So this is the line that we want to estimate. This is the actual observation. The difference is the residuals or errors. So we want to basically minimize the sum of a square of errors. Why don't we minimize the summation of errors? Because it's going to be 0. Then either we can do basically, just a moment. Excuse me. Either you can use a square or absolute value. Okay? If you use absolute value, it's not going to be sensitive to outliers. But in this class, we just use a square. Yep, go ahead.
Yeah, I was going to ask about outliers. Like, what if there's one
yeah.
outlier?
So if there is an outlier, this method would be very sensitive to outlier. Let me tell you something. So let's say This is the data that you have. So that's y and x. So this is the line. Okay. Now we don't have different color. Okay. So let's say we have one outlier here. Then your line is going to change something like this. Okay. If your data is, if you basically want to have a method which is not sensitive to outlier, then you need to replace the square with absolute value. But the problem with absolute value is the optimization is not that straightforward. Here, the optimization is very straightforward. Why? Because I can take a derivative. Okay, over there, it's not going to be that straightforward. Okay? Yes? Oh, when the error is correlated, then in that case, you need to do some transformation. You cannot use this method. You need to make some transformation to uncorrelate the data, and basically after that, do the regression. Yes. So you remember, so the question is whether we can detect if they are correlated or not. Okay. Yes, we can do that. What we need to do is, you remember in analysis of variance, we did some model adequacy checking to validate the assumption at the end of the day based on the residuals. We are going to do the same thing here. We are going to calculate the residuals, and then we see if they are uncorrelated, if they are they have constant variance, or if they are normally distributed. Yes. And in the regression class, actually you will see a method for dealing with correlated variables as well. Okay. Any other questions? Okay. So what we need to do for minimizing this, we just take a derivative, as you can see, equal to 0 with respect to beta 0 and beta 1. So we have two parameters. Take a derivative with respect to beta 0 equal to 1, and the other one with respect to beta 1 equal to 0. And then these are called least square normal equations. How many equations do I have? 2. How many unknown do I have? 2. Beta 0 and beta 1. So I can solve this system of equation easily, and these are the closed form solution for that. So your beta 1 hat is this guy. Okay, it's a little bit ugly. And your beta 0 hat is y bar minus beta hat 1 x bar. Okay? So what we can do, there is an alternative notation which makes it a little bit simpler. We define S sub xx, which is summation of xi minus x bar squared. That's easy to calculate. We call xy, which is summation of xyi yi minus this guy. This is also easy to calculate. Then I can write down beta 1 using these two new notations. So your beta hat 1 is xy divided by sxx. This guy divided by sxx. Okay? That's simple. And your beta hat 0 is y bar minus beta hat 1 x bar. That's it. Any questions so far? So this is the point estimation for intercept, point estimation for a slope, and this is basically your fitted regression line or estimated regression line. So as you can see, the model is okay. When you fit it, this is going to be estimated coefficient. This is estimated coefficient. So there is no epsilon anymore because we are talking about just a straight line. Okay? Does it make sense? Okay. So one example. I'll give you a couple of minutes to work on that. That's the same example that we have, purity versus hydrocarbon level. Everything is given. Try to find the fitted value. The fitted line. And also calculate predicted purity when hydrocarbon level is 1.01. By the way, I uploaded one paper on how to calculate, how to perform two-way ANOVA when we have unbalanced observations. I think one of you asked before. It turns out it's not very straightforward, but you can read to see how you can basically change the equations when the observations in two-way ANOVA is not balanced. So we have variable number of observations in each cell. Anybody got any numbers? Beta 1? No? Beta 0?
91.72.
Any other numbers? 74.28. That's about right. How about the predicted value? Nobody? Okay, so let's see. So we need to find SXY and SXX first. Actually, it's over there. The equation is there. So SXY, as you can see, is the summation of XIYI minus summation of XI squared. XY, summation of YI divided by N. So all components are given. Summation of XIYI is here. It's 2000 something. 2214.65 minus 23.92 times 1843.21 divided by N, which is 20. In this case, S would be 10.17. Okay? How about S of XX? It's the summation of XI squared minus summation of XI squared divided by N. In that case, I have 29.28 minus 23.92 squared divided by 20. This is 0.68. So our beta had 1 is the ratio of these two. 10.177 divided by 0.68, which is 14.95. So Our beta 0 is y bar. Y bar is 92.16. 0.95, and x bar is 1.1960. This gives me 74.28. Okay? That's beta 0 and beta 1. Very simple. So our line, fitted line, is 74.28 plus 14.95x. So that's the prediction line or fitted line. Okay? Any question so far? So the question says, what is the predicted value for (1.01). So I replace x with 1.01, then I calculate this guy. What is this number? 89.4. Okay? That's it. Any questions? So as you can see, 1.01 is not among these numbers. So you can use the fitted line for future prediction. But you need to be careful that the number that you are trying to predict for should be within the range of your estimation. So what I mean by that, you look at your x range, what is minimum and what is maximum, okay? And the number that you want to predict for should be between the minimum and maximum. So you can do sort of like interpolation, but you cannot do extrapolation somehow. Do you know why? You've heard this before, am I right? But do you know why? Anybody? The answer is very simple. You are just good guys. Listen to that. Say, okay, we do not do that. The reason is because we assume the linearity, and we verify linearity in this range. Maybe beyond this range, the shape of function changes. Okay? So let me give you one example. Okay? I'm just observing this part. I can say this is a linear function. Okay? But if I continue this, better, yeah. If I continue this linear function beyond the range that I observed data, then you can see there's a huge difference because of the shape of function. So you cannot do extrapolation unless you are sure that your function is going to be the same. Yeah, yeah, exactly.
I thought extrapolation was done pretty often.
Yeah, if you say, if you make sure that the shape of function, or you have enough data to capture the shape of the function, even beyond the basically range, then you can say, okay, with this assumption, you can do extrapolation.
How do you know, like, how many data, like, what your n is to have a good line, a good fit? Is there a rule of thumb or something?
There is no rule of thumb, but you can do hypothesis testing. We learned the statistics for that. So whenever you have larger n, the variance of estimate going to be smaller. Okay? So what I mean by that, how much faith you have on this number? I'm not sure. But if n gets larger, that number is more accurate. Because the variance of this estimate are going to be smaller. And you will see in the slides. Any other questions? So that's basically how n plays a role. Yes.
What's the prediction error for this question? Said that.
So the question is, what is the prediction error for? I can say the prediction error for this guy. I'm sorry, for not this guy, because this is new observation. For each of these guys, I can find. Do we have it? Oh, yeah, it's right here, actually. Yeah, I can say the prediction error is E is y hat minus y, or y minus y hat. That's better. Which is 89.54 minus 89.4. That's the prediction error. Any other questions? Good? Okay. So let's see how we can estimate the variance. So we just estimated, if I go back, that was basically the line. I told you how to estimate these two, but how to estimate this variance part. Okay? So basically, we learned how to estimate mu, but not variance. Okay? This is sort of like mu. Does it make sense? Actually, see if I have markers with different color. Thank you. So let's look at regression in another, basically with another point of view. So let's say we have data and they are replicated. Okay? So for each x, I have several observations. And I want to find the line, okay, which gives me the best fit. So I can say, let's say this epsilon I follow basically a normal distribution with that variance. So that would be one normal distribution. This is also one normal distribution. This is also one normal distribution. Okay? And the average of this normal distribution, variances are constant, which is what I said. But the average is not constant. So before you had yi follows a normal distribution in like previous examples, and you want to estimate mu and sigma squared, mu was constant. Now we say mu is not constant, is a function of another variable, which is x. Okay? So the expected value of y is a function of x. What is that function? It's beta 0 plus beta 1x. Okay? So basically, I can write down expected value of y given x is beta 0 plus beta 1x. So in terms of like distributional point of view, what you are trying to do here is trying to estimate the conditional mean of your response. What do I mean by conditional mean? Expected value of y given x's. That's what you are trying to do. Okay? So your y hat here or here is an estimate for conditional mean. Because your mean is not constant. It's a function of x. Okay? Just for clarification. So this is another kind of like point of view of a regression. Any questions? Okay. Now, the question is how I can estimate sigma squared. For sigma squared, I can find, first of all, I can find SSE, sum of a square of error. So each observation minus the prediction. So this is the prediction line. Each observation minus prediction. So we call this E, which is a good estimate of what? Epsilon. Okay? Then we calculate the square sum of a square, okay, and divided by n minus 2, it gives me what? The variance estimate. Do you remember the variance estimate for this case? What was that? You tell me. Summation of y minus y bar squared divided by n minus 1. Okay. Now, y is the same. So, y bar. This should not be y bar. Why? Because y depends on x. So instead of y bar, I have y hat, exactly, which is the prediction or point estimation of conditional mean. Does it make sense? The squared divided by n minus 2, not n minus 1. Why?
Two parameters.
What is it?
We have two parameters.
We are estimating 2 parameters. Here, we are only estimating y bar, which is 1 parameter. Here, we are estimating 2 parameters, beta 0 and beta 1. So we lose 2 degrees of freedom. That's why it's n minus 2. Can you see the connection here? Okay? So that estimator is very similar to SS squared. So now the question is there any easier way to calculate SSE? Yes. You can find SST, which is this guy, and then minus beta hat times plus xy. Then you get your SSE. Are we good? Okay. So we are done with simple linear regression. Now, what if we have more than one variable? So in this case, we have, instead of line, we have a plane. And that plane could be with some curvature when we have interactions. Or with no interaction, it's just a flat plane with no curvature. Okay? Any questions? Okay. So how we basically model this problem, we usually use the matrix format. So y, we define vector y, which is all observations in one vector. We define matrix x. The first column of matrix x is 1, all ones. This is for intercept. So let's say you have k variables. One is pressure, the other one is temperature, another one is yield, whatever, okay? So you have basically the values of x1. So x1, how many observations do you have? N observations for x1. x2, this is, let's say, temperature. This is pressure. You have, again, N observations, and so on and so forth. So you put it in a matrix. We call this matrix design matrix, okay, or matrix of predictors. You have your beta, which is the vector of coefficients, because the line that you want to estimate now in multiple regression is this guy. Beta 0 plus beta 1 x1, beta 2 x1i, beta 2 x2i, beta, here says k x ki plus epsilon I. Okay? We put all these k coefficients into one vector and all epsilons again in one vector. And this is kind of like a matrix form. So the matrix form of this guy, because you have different i's, would be this. Then, again, this is your least square objective function. You want to minimize it. If you take a derivative in like a matrix algebra, you can get the closed form solution, which is x transpose. As prime here is a transpose. X inverse x transpose y. Okay? Do you remember what transpose is? Everybody good with transpose?
What
Okay.
year was it?
Yeah. Just. So you don't change basically the diagonal. You just replace off diagonal. It's kind of like a mirror. So A, B, C, D. Transpose would be D, A, B, C. Okay? Agree? Hmm? Yeah, it should be. Let's see if you know it. A, D, B, C. Okay. Any questions? So X transpose X inverse X transpose Y, it gives you a vector of betas. One example here, let's say we want to estimate pull strength versus wire bond and the wire length. I'm sorry, pull strength versus wire length and die height. And so this is basically our design matrix. Everything is 1. How many observations do we have? I don't know, like, let's see if I know n here. Not really. 13 observations? Or no, it's more than that. Anyways, so we have this matrix, 2 variables, x1 and x2. This is x1, column for x1. This is column for x2. And these are y observations. So x transpose x, we calculate here. Then x transpose y is here. X transpose x, x transpose y. Inverse x transpose y would be this guy. So this matrix inverse times this vector. This vector here and this matrix here. Then we find beta 0, beta 1, and beta 2 because this is 3 parameters that we are estimating. And this is our basically a line, estimated line. So what if I want to have x1 times x2? What's going to happen? I have x1, I have x2, I have 1s. These are all 1s. x1, x2. I need to add 1 column, which is x1 times x2. Then you get 1 more coefficient for x1 times x2. Any interaction that you want to add, you add 1 column, which is basically the multiplication. If this is 2, 3, this is going to be multiplication of 2 and 3, which is 6. Does it make sense? Okay? So you just expand your design matrix. What if I want to have one example like this? Beta 0 plus beta 1, x1, beta 2, x1 squared. This is also multiple regression. Okay? Although you have 1 variable, but in reality you have more than 1 variable. 1 variable is this guy, 1 variable is this guy. So what you do, your design matrix, again, is 1s, x1, 2, 4, 5, whatever it is, and x1 squared, which is 4, 4 squared 16, 5 squared 25, and so on and so forth. Yes?
Is it safe to say that your number of betas will always determine how many I guess, non-one fields?
Yes. The number of betas that you have is the same as the number of columns that you need. Okay? Okay. Now, do you have any questions so far? No? Let me ask you a question. So beta 0 plus beta 1x. This is simple linear regression. What is this guy? Multiple regression? Linear or nonlinear? Nonlinear. Everybody agrees? This is linear regression. Okay? Why this is linear regression? Because I can replace x1 squared with some variable called z and still use the concept of linear regression. Okay? So the form of function that you have is nonlinear, but the type of regression is linear regression. So the linearity is defined with respect to betas, not with respect to x's. Okay? That's important, basically, difference between linear and non-linear regression. So what I mean by that, as long as your function this is linear because it's linear with respect to betas. This guy is nonlinear regression. Okay? Because it's nonlinear with respect to, again, betas. Does it make sense? Why we don't call this nonlinear regression? Because we can easily transform it to a linear regression without changing any structure.
It's a nonlinear predictor?
Exactly. So it's, again, it's a nonlinear functional form. Even if they don't call it nonlinear predictor. They call it linear predictor. Why? Because at the end of the day, your predictor is what? Your predictor is x beta hat. That's linear. Okay? It's a nonlinear functional form. But we call it linear regression, linear predictor, whatever. Does it make sense? Any questions? So we have 3 minutes. Okay. How we can estimate the variance for this example? Actually, we had 25. N was 25. So what we do, for each observation, we can estimate the prediction. How? For example, for the first one, let's say the first one is x1 is 2 and x2 is 50 and y is 9.95. So we can easily find y hat, which is 2.26 plus 2.74 times x1 plus 0.0012 times x2. I'm sorry, x2 is 50. Then it gives you y hat. In this case, your y hat is 8.38. Okay? So you can find the residual or the prediction error for all of them. And then square them, add them up, divided by n minus p. What is p here? I'm using p and k kind of like interchangeably. So it's the number of coefficients to estimate. In this case, the number of coefficients is what? 3. You are estimating 3 coefficients. Okay? Any questions? I guess I stop here and then continue later on with some property of multiple regression. Let me see. Yeah. If you haven't sent me your abstract, please do so through email. And we have exam on April 15th. Okay? 15th. Yeah. In 2 weeks. Yes, you. Yes.